now that we've talked about the dot product, I want to move on to another useful vector operation, which is the cross product. You'd also hear it referred to as the vector product, and that is because it returns a vector, unlike the dot product, which returns just a number. When you put in two vectors as an argument to the cross product, it will return a vector. So in this video, I want to explain what that vector is and what the cross product actually comes from. I personally feel like these formulas for the cross product, when you get too much into them, you forget what the cross product actually does and where it comes from. So that's what I want to explain in this video. So where does the cross product actually come from? A good way that I found that this question arises is if you're given two vectors A and B. I don't want to write U and V anymore because I feel like my handwriting, it makes them confused between. But given two vectors A and B, let's say we want to find a vector that's perpendicular to not one, but both of the vectors. It's important to note that any vectors, when they're put tail to tail, it's guaranteed to have a vector that's perpendicular to both. But not all lines in space will have a line that's perpendicular to both of them. But when you do put them tail to tail, unlike say they're skewed, they won't have a perpendicular line to them. But in this case, they do. But anyways, when you ask the question, how to find the vector that's perpendicular to both of them, you also have to consider that there's an infinite amount of vectors that are perpendicular to both. If you can see, imagine this dashed line as the set of all vectors that are perpendicular to A and B. How do we actually compute the cross product? Remember that the cross product is perpendicular to both A and B. And what we learned in last video from the dot product is that when the dot product of two vectors are equal, are zero, then they're perpendicular. And also remember that the dot product can be written in terms of the components of the two original vectors. So here I've written out what I just said. This first line says A dotted with Z equals 0 and B vector dotted with C vector equals 0. C is our cross product. Remember that what we're given is A and B in terms of their components, and what we need to find is each component of the cross product. So given the dot product of these two dot products, I want to write them out in their component form. Okay, now that I have the expanded component form for each dot product, what I'm going to do now is in this first equation, which is A dotted with C, I'm going to multiply that by the K component, or the third component of the B vector. This equation incorporates the A and C vector. Now I'm going to multiply by a component of the missing vector, which is B. And same thing for this equation, which is B dotted with C. The missing vector is A, so I'm going to multiply that by the third component of the A vector. You don't have to do the third component each time, but it'll eventually show why and how it'll give you the same answer, but you arrive there in different ways. This is not a pretty looking system, but it's important to stay organized. The way I wrote it is I kept A, B, and C. That's the convention that I wrote each term in. So put A, B, and C, and if the letters are consecutive, then just order them by numbers. That helps me. But now that I have this system of equations, what I'm going to do is I'm going to subtract this second one from the first one. Okay, this equation does look a little bit nicer. Notice that these terms right here that have the third component of the C vector, they canceled out, which is nice. But now we have this equation. We're not done, but it tells us something that's pretty important. Remember, what we know is that are the components of the A and B vector. In each of these parentheses, that's what we have. We have our knowns, and then what's multiplied by them are what we don't know, which are the first component and the second component of the C vector. it's one equation and two unknowns, which means that there's going to be an infinite amount of pairs with these two unknowns that satisfy this equation. And again, there's an infinite amount of vectors that are perpendicular to these two. This kind of conveys how that's also true. But what we can do is we can pick two values for these unknowns that will satisfy this equation. First, I pick C1 to be this first term right here, and then C2 is going to be the negative of this term right here, because we have this times this minus or plus the negative of the same thing, which is just going to be 0. If you have something plus its own negative, it's going to be 0. But hopefully this right here makes more sense than what I said. So if you want to plug these back into this equation, you'll see that it will satisfy this equation and will equal to 0. So now I've picked these two values that satisfy this equation. Now what I'm going to do is we still need the third component of the C vector. We only have the first and the second. So to get that third component, I can substitute back into either of these original equations. Now that I've substituted the picked values for C1 and C2 back into the original equation that we started with, I arrived at the ultimate value for C3, but I want to explain each of these steps. So first, obviously, I substituted C1 and C2. Now remember, what we're looking for is C3 in terms of what we know. We don't want to use other unknowns to find an unknown because that doesn't make sense. So basically what we know is the components of A and B, and we're going to use that to find C3. So if you want to solve this equation yourself, just remember that you want C3 on one side of the equation equals things we know. So, right, I expanded it, and then I want to focus on this part right here. I don't know if you can see it, but basically it's A3 multiplied by a quantity equals 0. Now, if you remember from, I think, Algebra 1 or Algebra 2, when you have two things multiplied by each other equals 0, that means one of the products equals 0, or other product equals 0, or both of them. Now, the next step after this, what I did was I divided both sides by A3. And remember, if you divide two sides of an equation by a variable, it's under the condition that that variable does not equal 0, because if you divide by 0, that's undefined. Remember, the first thing we did was we canceled out C3. That was the first thing we did. We multiplied each equation by the third component, or by A3 and B3 respectively. And what that did was that canceled out C3, and C3 is the final thing we solved for. Now, like I said, you didn't have to do that. For example, you could have multiplied both equations by A2 and B2. Eventually, whichever one it would have canceled out. It would have canceled out either of C1 and C2, and C2 or C1 would have been what we eventually solved for. So basically what I'm saying is, whichever path you decided to take, you would have canceled out a different component of C, which is what we're looking for. And what this is saying is, it's not saying that A3 can't be 0, because it could be. This could be 0. But what it's saying is that A3 and A1 and A2 can't all be 0, if that makes sense. If the A vector was 0, 0, 0, then it'd be the 0 vector, and when you take the cross product of it, it will technically still give you 0, because anything cross the 0 vector, which I'll show later, is just 0. It'll make sense later. But what this is saying, it's not saying that A3 can't be 0, but it's saying that the entire vector can't be 0. Hopefully that makes sense. But again, it just depends on where you started from here. So once you divide it by A3, it'd give you the final value for C3, which is a combination of terms that we do know. Now, given the value, remember we started with values for C1 and C2. Now we know a value for C3. Therefore, we know the full vector for C, which is the cross product. This right here, which from the values that we conveniently picked for C1 and C2, this is actually the cross product, how it's defined. Again, this is one of infinitely many vectors that are perpendicular to A and B, but these values right here, they are the cross product of. Now we have a representation of the cross product when we're given two known vectors in terms of their components. How can we get the vector that represents the cross product? Remember, these are all constant. These will eventually be constant. So there's a vector with a set length and direction. But now I want to introduce something called the determinant. Obviously, this form is not very nice. It's honestly not going to get any easier, but the easiest step away from this is knowing what the determinant is. So if you've ever taken a linear algebra course or multivariable course, you know that the determinant of a matrix is another operation that shows up in a lot of applications such as this one. So the determinant itself, it's pretty arbitrary. It's when you have matrices and you do this certain operation that I'll explain. But it's basically, don't try to look too much into where the determinant came from. It so happens that when you do this operation to matrices, they show up a lot. It's like asking where did addition come from? It's just addition. You can't go any deeper than that. But yeah, basically, say you have a 2 by 2 matrix and you want to take the determinant of that. Basically, what you'd be doing is you take the product of the diagonals and then you subtract it. So for a 2 by 2, you take the first diagonal going top left to bottom right, and then the second diagonal from top right to bottom left, you subtract the second one. As you can see, you have A, B, C, D. First diagonal is A, D. Oh, sorry. Yeah, it'd be AD minus CB. So now taking it to a 3 by 3 matrix, it's pretty much the same thing, but I visualize it differently. You could do diagonals minus diagonals, because if you want to look it up, it's like taking these diagonals this way are positive, and then these diagonals are negative. But the way I like to visualize it is, say, the first thing you do is you go with this column. You don't use anything from the first column. And then you look at this box right here. You're going to take the determinant of this box that's not in this column, which is, yeah, like this 2 by 2 determinant. And then the second term would be when you don't use the second column and use the determinant of the remaining values below it, which is here. Hopefully my colors make sense. But yeah, and then you don't use the last column, and then you take the determinant of what's left, which, yeah, you'd have the top values times the determinants of the bottom values, and then add them all together, you get a number. If these were all numbers, the determinant would give you a number. But if you look up here, the values weren't numbers, but they were vectors. Each row represented a vector with I, J, K each being the unit vectors with length 1. And then you have the A vector, B vector, and this determinant would give you a sum that has coefficients I, J, K. This determinant is the C vector. That's the simplest way of explaining how to use the determinant to find a cross product. That was the algebraic definition of the cross product and by its components, but like the dot product, I want to connect it to another representation we have, which is the geometric representation. First, I want to talk about area of parallelograms. This will be important later, but notice, say we have A and B again, and we look at the parallelogram that's spanned by these two vectors. So you have this vector, make a copy of it, and add it tail to tail with vector B, and do the same thing with a copy of vector B. And then you have a parallelogram. And what I want to do is I want to find the area of this parallelogram. Remember, area of parallelograms are the base times the height. And in this case, the base, let A be the base, or the magnitude of A be the base, not the vector itself. So, and now we just want to find the height. And because if we're given an angle between the vectors A and B, I want to take this right triangle when we drop the altitude or the height from vector B. Now we have theta and the magnitude of B, which we know. We don't care about this side, like the dot product, but yeah, all we need to know is the magnitude of B and theta. So looking at this opposite side of from theta, which is the height, let's say that we know that sine of theta is going to be this height divided by the hypotenuse, which is the magnitude of b. So it would be sine of theta is equal to h over magnitude of b. Rearranging for h, it will give h equals magnitude of b sine of theta. So that's our height. Now all we need is to put it back into the area formula to give area of the parallelogram equals base times height, which is the bases we know magnitude of A, and then we just found the height, so the total area will be magnitude of A times the magnitude of B sine of theta. So back to the cross product that we just found. Reference this right here, the component representation of the cross product. What I want to do is focus on the magnitude of that vector. We can, using distance formula, the sum of the squares of each component is equal to the square of the magnitude, or the magnitude is equal to the square root of the sum of squares. And basically, I want to get rid of the square root just for my sake. I'm not gonna lie, don't even try following this because I also had to find it on the internet. But basically, what I did was I expanded this side to get to this, and don't bother trying to figure out how to get from here to here. But just know that in the end, it simplifies to the sum of squares for the respective vectors times, well, this is the sum of squares for the components of A, sum of squares of the components of B, and then this part right here. But the important part to get from this is that this right here is actually the square of the magnitude of A. As you can see, the square root of all this would be the magnitude. The square root of all this would be the magnitude of B. And this right here, well, this is actually the component form of the dot product between A and B, which is also nice, and then squared. So if you can see it, if you want to follow along with all this, you can see that. But what I wrote was that the left side of the equation was, this is the magnitude of the cross product squared is equal to the magnitude of A squared times the magnitude of B squared minus the magnitude of the dot product squared, or the dot product squared. So there's more simplification to do, so I'm gonna erase all this. Okay, now with starting from here, basically what I did was the geometric form of the dot product AB cosine theta, I substituted for that. Right here, AB cosine theta shows up and you can factor it out. And then it'll eventually give A squared magnitude of A, magnitude of B squared times 1 minus cosine squared of theta. And using the trig identity, which is cosine squared plus sine squared of theta equals 1, this can be written as sine squared of theta. And now you have the magnitude of the cross product squared is equal to the magnitude of A, magnitude of B sine theta squared. And obviously you can take a square root, which will eventually give you the magnitude of the cross product is ultimately the magnitude of A, magnitude of B sine of theta, which is what we found here. Now, what does this mean? This means that the magnitude of the cross product of vectors A and B is equal to the area of the parallelogram that they span. Pretty much the distance of a line is equal to the area of a two-dimensional quantity. I know that's kind of hard to visualize, but yeah, you have length is equal to area. The same way you can have a meter stick of length 1 meter, and you have a square box or cube with length 1 meter. The meter stick has a length of 1, and the cube has a volume of 1. See how they have the same magnitude, but it's obviously not the same quantity. But in this case, yeah, that's pretty much what this is saying. You have a length that's equal to an area. And yeah, so that's pretty cool. One thing I haven't talked about is this part of the cross product right here. This is the n vector. So basically, we know that this right here, AB sine theta, is a magnitude. But at the end of the day, the cross product is still a vector. So we need a vector attached to that magnitude because you have a magnitude, and then, but you also need a vector to multiply that magnitude by to get the cross product. And basically, n is what we call a unit vector. A unit vector is any vector with magnitude of 1. It doesn't mean that each component is 1, but the magnitude is 1. So I, the vector I, which is in three-dimensional space, it'd be 1, 0, 0. That's the same thing as like the x-axis, because if you let this is equal to I, this equal to k, and this equal to, wait, my bad. This is j, and this is k. These are each unit vectors which respond to each of the Cartesian directions in 3D space. So yeah, a unit vector has a magnitude of 1. And if you have a magnitude of 1 multiplied by a magnitude of whatever, it'd be that magnitude that you multiplied by. So this vector it has a magnitude of 1, but you don't necessarily know its components. Its components are actually what tell you the direction that the vector is going in. Say, if you think of a triple of numbers that if you took the square root of their magnitudes, say that their components, it'd be this square root. So if a vector has components a, b, and c that satisfy this equation, then it's a unit vector. For example, the easiest one would be, again, the unit vectors 1, 0, 0. 1 squared plus 0 squared plus 0 squared is 1. Square root of 1 is 1. There's an infinite amount of vectors that have a length of 1. If you took all of them and plotted them, it'd actually make a sphere with radius 1. But yeah, hopefully that explains what this vector is doing here. Again, it's just being multiplied because you have a scalar multiplied by a vector, and that'll eventually give you the direction that you're going in, as well as how far you go in that direction. Remember that there's an infinite amount of vectors that are perpendicular to two vectors put tail to tail, and you need to know which direction. If you don't care about the magnitude, at least you'll sometimes be asked what's the direction. It could be, like in this case, this could be up or down from the vectors. So if you just want to know the general direction of the cross product, you can take your right hand and you start the order of a cross product matters, which I'll also talk about. So you let your fingers be the starting vector, and then you curl it towards the vector that you're resulting in. So in this case, the starting vector is A, and I'm curling it towards the B vector. And wherever my thumb points at the end of that's the direction of the cross product. So if I did B cross A, that means I'm starting with B. That's where my fingers represent the B vector, and I want the orientation to match the operation. So I can't curl it this way because that's not where B and A are. B and A are going like this. So I need the curling to be your fingers can only curl, or my fingers can only curl this way. So I need the curling to be this way, and where my thumb ends up is down here. In general, the cross product is not commutative, meaning that the cross of A onto B is not the same as the cross of B onto A. In actuality, it's the negative of each other. So yeah. If you switch the order of operations with a cross product, you end up with negative vectors that are negatives of each other, but they do still have the same magnitude. So in the parallelogram case, technically you can't have negative area, but you need to be consistent with this idea. So you'd have a negative magnitude, and basically it'd just be saying like, what's the area between this parallelogram and this parallelogram? These are the same exact parallelogram, but they're just flipped. So same magnitude, but different orientation. We now understand what the cross product is and where it comes from. as in how you can calculate it and what it represents. We know the geometric and algebraic representation, but now I want to talk about some actual applications of the cross product. So first, let's talk about the limits of the cross product and the special cases. So firstly is the the case where A and B are parallel. Parallel meaning they don't have to point in the same direction. They can also be anti-parallel, as in parallel, but pointing in exact opposite directions. So that means the angle between them is either 180 degrees or 0 degrees, and they lie on top of each other. So with that, that means the magnitude of the cross product is AB sine of 180 degrees or sine of 0 degrees. And either way, that value is 0, which means the cross product is equal to 0. That makes sense because if you have two vectors and you want to take the area of the parallelogram spanned by them, if they're straight, the area there is no. It's a one-dimensional parallelogram, so there basically is no parallelogram. Therefore it has an area of 0. Same thing as if they lied on top of each other. The second case is when they're perpendicular, such that this follows the right hand rule. These look like the same case, but they're actually not. So in this case, they're perpendicular, but they're in this certain orientation when they follow the right hand rule. I say follow right hand rule, but it's when the cross product is positive. So AB sine of theta would be AB sine of 90, or in this case, sine of 270 degrees. Again, the cross product, it depends where you start from. That's why these are different quantities. So it'd be AB sine of 90, and sine of 90 is 1. That's the maximum value of the sine function. So it'd be the magnitude of the cross product would be AB. In this case, this would be the negative magnitude. Again, the cross product, the magnitude of the cross product, it lies between the range of the negative product of the magnitudes and the positive product of the magnitudes. And these three cases are where it's the minimum value, 0, and the maximum value. So, where does this actually show up in real life? One way that you will commonly learn it is the application of torque. Torque is pretty much the rotational equivalent of force. Like the linear equivalent is just force creating motion. Units of torque, you would find that it's newtons times meters, not just newtons, which is the unit of force. The total torque on about a pivot, say this is like a bolt or a nut, and this is a wrench that I tried to best draw, and you have a force that's applied to that wrench about this axis. So the torque applied would be the cross product between the displacement vector and the force applied at that displacement vector, which would be the magnitudes of either times the angle that you're applying it at. Another good example is when you try to open a door. You open a door as far away from the pivot as possible to make it as easy as possible and apply maximum torque to the door. Obviously, say if this was a wrench, I wouldn't be pushing parallel to the displacement because that would actually be 0. Again, when the vectors are parallel, the cross product is 0. I get max. It's easiest to push the wrench perpendicular to the displacement vector. Obviously, when it's spinning around, it's hard to keep it perpendicular throughout the whole motion, but that's how we optimize like rotation. But yeah, that's the cross product and its applications, where it comes from. But hopefully that made sense.